All right, so good evening and welcome back to another lecture of cloud computing for the winter 2023 semester. So last time where we had left off was basically with our discussions on virtualization technology, right? So some of the important concepts that we had covered back then was basically have to get an understanding of what is virtualization as a technology, the formal definition of it. We all have a intuitive understanding of virtualization means, but we discussed specifically about the keyword-based definition of what virtualization entails, right? We also talked about the motivation behind virtualization. Why would somebody want to do virtualization to begin with? And then what is the benefit with the knowledge of how computer clusters are developed and so on and so forth. And then we talked specifically about the hypervisor or the virtual machine manager. That is basically the essential software that was developed to actually implement virtualization as a technology, right? So that is the important thing that is around the concept of hypervisors or VMM, right? So it is like interchangeably used, but the most popular term is hypervisor. And we kind of discussed about the different layers on which you can implement virtualization technology. And that kind of goes back to our understanding of what are the different layers in a traditional computer system, right? And then where you can apply the virtualization technologies. So we talked about the fact that there are 5 different layers of virtualization abstraction levels, right? So this is where you can apply the virtualization technology, and depending on where you apply it, there is a pro and con. There is a benefit or a disadvantage at each layer, right? So we talked about the fact that you can apply the virtualization on the instruction set architecture level, or you can apply it directly within the hardware, which makes it the hardware abstraction layer. And then the more optimal or the reasonable layer, which provides us a balance between how difficult it will be to implement virtualization, and then what benefits we will get out of the virtualization technology, and that being the operating system level virtualization. And then finally, you had 2 more layers above the OS layer, which basically is the library level, where if you are trying to use different types of application programming interfaces and you need to provide an isolated environment for every user who uses it, or provide them with a platform in order to execute their programs, processes, whatever it is that they're trying to execute in that virtualization environment, and that is basically the library level. And then finally, at the very top, we have the application level, where you are basically providing through virtualization different conceptual capabilities such as application isolation, which is also sometimes called as sandboxing, right? And then we did an analysis of the performance with respect to applying or using these different virtualization abstraction levels. We discussed it based on different performance metrics, such as which gives us the best performance, where do we get the most application flexibility, which is the most costlier in terms of implementation, and then where do we get the maximum amount of application isolation, right? And then we kind of led our discussions from that point onwards to get an understanding that for the more popular service model that cloud computing essentially has, which is in the form of software as a service, platform as a service, and infrastructure as a service. And we will discuss about these 3 service model again in chapter 4 when we start discussing the cloud computing architecture itself. And we talked about a mapping of where in these popular service model, or what type of virtualization abstraction layer is primarily used for these different types of service level, wherein we kind of came to this conclusion that if we are looking at software as a service, then it's mostly going to be using the user application level of virtualization. Similarly, for platform as a service, we had OS level kind of integrated with runtime library support. And then hardware virtualization levels primarily supports infrastructure as a service, in addition to all the other available abstraction layers, right? We discussed about the requirements, the design requirements of hypervisor, because remember, the importance of the hypervisor essentially runs through the idea that for any layer, wherever you're trying to implement it, the most reasonable way of implementing virtualization as a technology is through software emulation, right? And the software that is specifically designed to enable this technology is hypervisor itself. So we talked about the fact that if you design a hypervisor or a VMM, then whatever program or processes that will be allocated to that virtualized environment should be identical in terms of its execution as if it is running on its own standalone traditional computer, right? So that is one of the basic key requirements of a hypervisor, right? And its implementation. There are, of course, exceptions to this rule of when you can have exceptions in terms of performance of an execution of a program running within a virtualization environment. And that is when you have a thrashing or page thrashing kind of scenario as that you have in operating systems, where one of the processes is taking too much of time, too much of resources, and then it's a question about the availability of the entire system. Then there can be some exceptions that is made. Or if a program is kind of stuck or frozen due to some sort of timing dependencies, not because of a fault of its own, but it's waiting for data or something like that, then it can be kind of pushed down on the priority list of its execution of how much resources is being given to it, right? And then the last thing that we discussed was basically the two different types of architecture that we have for hypervisors. So the first one is known as type 2 or bare metal hypervisors, which is the more popular choice amongst cloud service providers, right? And then there is type 2, or better known as hosted hypervisors. And the distinctive feature between type 1 and type 2 is the fact that type 2 is implemented on top of the host operating system, right? So if you have a traditional machine, then you will have the hardware layer at the very bottom, right? And on top of that, you will have a host operating system. And then on top of that, if you implement the hypervisor, so that the control of the hypervisor for the underlying resources needs to go through the host operating system, then that is known as a type 2 or hosted hypervisor. And then similarly, in contrast to the type 2 or hosted hypervisor, if you are looking at the architecture of type 1 or bare metal hypervisors, then the hypervisor is directly responsible for controlling the underlying asset, which is the hardware resources that are available. And on top of that, the VMs execute similarly, right? So we discussed about which is a more reasonable choice of implementation, that is whether you should use type 1 and type 2. And of course, remember, there is no black and white answer to these type of questions, right? It is always a discussion. It is always subjective in nature. And we had this discussion with respect to which is more secure, which gives us better latency, and then when would you choose and what type of architecture would you choose, right? And then finally, we had this discussion about hypervisors versus container. It's kind of like a trapdoor question, essentially, because both are creating some sort of isolated environment, but what they are actually implementing from a conceptual standpoint is different, right? So hypervisors essentially are running independent of the underlying operating system. It is running the OS and then allocating those different guest OS on the VM platforms that will be created on top of that, right? And then the containers is basically running independent of the OS itself. So it's just creating a platform environment that runs within a particular VM, right? Or maybe within the local machine itself. And then they are providing all of the different library support or applications that is necessary in order to execute a particular type of process or a program, right? So what is essentially required to make the container executable is what is known as a container engine. So as long as the container engine is present either within the VM or in the local machine itself, then whatever container that you're using will be able to execute all its feature based on which it has been loaded, right? So coming to the discussion for today, what we want to talk about is basically to have this discussion is like when cloud computing architecture was established, right? What type of virtualization level or virtualization abstraction layer was adopted, right? And this goes back to, of course, we did this mapping here when we did the performance analysis and stuff like that, right? But the trip that you want to take down the memory lane is to understand that, okay, everybody saw these different layers of virtualization technologies, right? And then everybody was kind of akin to the fact that how the performance varied for these different performance metrics, right? And through that, there were two choices which was quite evident in order to implement the architecture of virtualization, right, as a whole, and not for specific pieces. Like infrastructure is a separate piece, platform is a separate piece, software as a service is a separate piece. But instead of talking about these separate pieces, right? So if you want to build the cloud computing architecture itself from the very bottom, from the very scratch, right? Then where should you start implementing the virtualization, right? So the two evident choices that was available to the service providers was OS level virtualization or hardware level virtualization, right? So what we want to talk about is basically what is the idea of OS level virtualization? How does it contrast with hardware level virtualization, right? And what made cloud computing finally choose neither of the options, right? So essentially, this is why this discussion is a little bit interesting, is because it talks about the benefits and maybe the disadvantages, a little bit of the drawbacks of both the available options. But at the end, we would be able to appreciate why neither of those options were selected, okay? And something in between was essentially designed or people came up with, and that was finally adopted to start off with the cloud computing architecture that we know for today's cloud service providers, okay? So OS level virtualization kind of is pretty straightforward, right? The whole idea of the cloud computing architecture rests on this one cornerstone fact that the users should not be responsible for basically gathering their own computing resources and then having to manage and maintain them, right? So this is the primary idea of our cloud computing or basically service computing or utility computing. Remember, these were the two different terminologies that is used to refer to cloud computing as well that came into being, right? It is a little bit different. And the reason why it is a little bit different is the fact that, of course, we talked about the fact that when grids were there, right? Either these are computational grids or data grids, right? And then if you apply the virtualization technology, okay, coupled with the concept of elasticity, we talked about from that paradigm shift chart that this gave rise to cloud computing, okay? But cloud computing the cloud computing itself is an architecture, right? It's a design paradigm, okay? So essentially, you can have what is known as public clouds versus private clouds versus hybrid clouds, right? That is the architecture that you will see that there are different types of way in which you can implement these virtualization and elasticity technologies on top of the grids, right? So, but in addition to that, there is also another spectrum where the discussion is about the architecture of another form of computing that is known as service computing. Okay. And this specifically applies to public and hybrid clouds. Okay. Either public or hybrid clouds. The private clouds are a little bit of a different entity because it differs or distinguishes itself from the core ideology of service computing. Okay. And what that core ideology essentially tells us is that whenever a user wants to use any sort of service, right? And that service could be hardware related, it could be executing a process or just using a particular application, then they should not be responsible for owning any of the hardwares that or the computing resources that are essential for its execution, for whatever their purpose is, the execution of the purpose, let's put it that way. They should be not responsible for having to manage or maintain any of these computing resources as well. So that is where the idea of service computing and utility, or sometimes this is also known as utility computing, comes from. That is the core notion behind these two computing architectures, right? And they are kind of ingrained within the architecture of public and hybrid clouds, right? So in hybrid clouds, you are still responsible for partly owning some of the hardwares and managing them and maintaining them. But in public clouds, like the ones that we know in this day and age, like AWS or GCP or Azure, these essentially liberate its users from having to own the hardware or having to manage it or having to maintain it, right? So all you do as a user is stay focused on designing and developing your app, right? Or whatever it is that you're trying to do using their resources. And then you pay as much as you use. So that is where the service or the utility part comes into the picture to the cloud service providers, right? So that was essentially the goal of cloud computing, right? So there is also another third type of cloud computing architecture implementation, which is known as private clouds. But the only difference here is that a very large company, let's say like HP or Microsoft, they build a cloud computing architecture for their own company, and their employees are only allowed to use the computing resources that has been pooled together, right? So there's still an idea of, there are a few things that are kind of like roaming here, right? It's basically pooling the resources, okay? And this is coming from computer clusters, right? So if you pool them specifically for the purpose of computationally intensive applications or high throughput applications, then it becomes like a computational grid. And then if you're storing the data on these pooled resources, then you are looking at data grids, right? And along with pooled resources, we are looking at virtualization. So this further enables resource sharing, right? The pooling resources brings together the scalability factor. Virtualization further improves the scalability factor by improving resource sharing. And then you have the concept of elasticity, okay? Which basically kind of plays into this whole idea of not having to manage the computing resources. Because if you think of elasticity, it factors in directly with scalability, scaling up as well as scaling down, right? So in private clouds, the only thing is that the users are the employees, right, of whatever organization decided to implement that. So that is where the notion of cloud computing comes into the picture, right? And one of the two problems that people initially faced when they were trying to implement this cloud computing architecture was, how do you actually implement the concept of elasticity, right? Which also is known as on-demand dynamic allocation of resources. So we talked about the web server example probably a few classes back, right? We're talking about load balancing and stuff like that. It's like, if the demand goes up, how do you take care, or how do you handle that rise in demand in a dynamic manner, right? So that was one of the initial challenges that was present there. And then the other problem was, if you're going to apply virtualization, whether that is, let's say, irrelevant of where you want to apply that virtualization level, right? It doesn't matter OS, hardware, or ISA level, or application level, or runtime library level. The problem there was, how do you set up or instantiate all these new virtual machines, right? Which will share some of the common computing resources, underlying computing resources of the hardware on top of which it is being instantiated, right? And basically the reason why this was difficult is because instantiating a VM at the very beginning was a pretty slow operation. And the reason why it is slow is because you essentially are looking at booting an entire system, okay? Because remember, from our perspectives as architects, we are thinking in terms of, okay, virtualization as a technology, you take a chunk of the underlying resources, and then you multiplex that, share it amongst different users, right? But if you think from a user side, right, they need to, basically what we need to create for them is something which is similar to like a local computer. Right? And every time you use your local computer right now, hardware technologies is improved by a lot, right? So you have the options for solid state drives, which kind of improves the booting by a lot. But if you think 10 years back, right, or even 15 years back, when people were still trying, we didn't have solid state drives and stuff like that, booting was a challenging issue. And every time you wanted to create a VM, you are basically allocating a machine to a new user. So that will entail the process of booting, right? And how do you take care of the fact that, okay, what happens if this machine crashes, right? Then we need to provide some level of fault tolerance. And when you're thinking in terms of fault tolerance, So now you have to basically create replicas of the virtual machine templates, okay, that needs to be present, so such that if the initial VM that has been, instantiated for a particular user, for whatever reason fails, right, either due to the failure of the physical resources, underlying physical resources, or due to loss of connection from the user side, or even from your side as a service provider, then what do you do? Because if you notice, the primary motivation is that you want to shift the responsibility of managing the underlying resources or whatever computing resources are being dispensed to third parties. Third parties essentially means service providers. Okay, so that is what SP stands for, the service providers. All right. So that means it is our responsibility as a service provider to provide fault tolerance, right? And this again goes back to how do we replicate the VM templates? Where do you store them, right? Because this is essentially going to be an image that will be used for booting a new virtual machine if the primary machine fails, right? So that creates a problem, right? And the last challenge that was there is, let's say the user is in the process of using a particular virtual machine environment. Let's say they have installed some of their applications that they need. They have executed some processes. It has generated some intermediate results, some intermediate data, and those kind of operations, right? This kind of daily stuff that you do on your local computing machines and stuff like that. So if that happens and then the machine fails at a certain instance, what happens to all those data, right? So there is this question of keeping a track of the state of VMs. Okay, and later on, we will learn that there are different storage technologies that are available that you can associate with your virtual machines, which are categorized as persistent storage. And then the other category is known as, of course, non-persistent storage or ephemeral storage. Okay, so the problem that was there is, how do you keep a track of the current application state? Okay, so that if anything happens and that you need to move from your parent VM that was initially instantiated and you need to kind of migrate that to one of its replica after booting another VM machine, how can you restore the state of the machine, right? So that is the whole idea or some of the challenges that was basically faced by service providers when they were trying to basically implement the virtualization technology on top of computational or data grids, right? So, of course, there were two options. There was the hardware level option, and then there was the OS option, which came out on top of the other options with respect to the balance that it provides in terms of its performance, isolation, and then cost of implementation and things like that, right? But the hardware level, as we had discussed it before, right, when we were doing the comparative analysis of the performance study, is when compared to OS itself, is a little bit slower, right? And it's also a little bit more costly. Okay? And the reason why we say that is because, first of all, if you want to implement hardware level virtualization, then you have to modify the actual hardware that is already out there, right? So this hardware modification that needs to be performed in order to implement the OS level virtualization is essentially costly. Okay. There's also an issue about proprietary. Okay, because all of the different hardwares that was available on the market at that point of time, the commodity hardware, it was made by a specific company. So you cannot just pick it up and start modifying, right? It's not going to help you out there, right? So that is the reason why we were not, as service providers, able to implement full virtualization on the hardware level itself, right? And the other problem was that if you think of a hardware, right, it's essentially a limited set of resources. That is, in terms of partitioning it, you can only do partitions into so many chunks. So this is not about multiplexing anymore, but this is creating a virtualized environment and then providing it to the different users, right? So how do you boot up a particular partition for a particular user? And let's say then the user is gone, then you need to basically reset this partition and then recreate this for the next user based on their requirements, right? So that is basically a very slow process when you're trying to set up a virtual machine environment directly on top of the hardware level virtualization, okay? In addition to that, storage becomes an issue because you have to take this entire chunk of your hardware partitioning, which essentially is virtualized at this point of time, and then you have to find a way to store it somewhere. So that kind of creates an overhead in terms of maintaining the VM templates, okay? And then if you kind of keep storing all of the different VM templates for initializations that has been created on the hardware level, then another problem which becomes an overhead on top of the storage is how do you keep track of the overlapping contents, right? Because if you think about it, we just talked about the fact that, okay, this initial VM partition that was created on this hardware level was, let's say, given to user one. We talked about the issue that once user one moves out and user two comes in, okay, you need to kind of reset this environment based on the requirements of user two, based on the VM requirements of user two. But what if down the line, there is another partition here for, let's say, user K, okay? And there is an 80% match of whatever the requirements of user K is in terms of their virtual environment was matching with user one initially. Okay, so if you save both of user one's template and user K's template with the thought that later on, if some other user comes and wants to use a similar kind of configuration, then we can simply just load that to that particular VM environment slot, right? But due to this commonality between the two different templates, you are using up twice. You're basically using up 80% more memory, 80% more storage, not memory, sorry, to keep the virtual machine templates, right? And the problem that this causes is because there is no way to track what is happening inside the virtual machine states, right? So you don't know how much overlap is present or how much distinction is present between the multiple VM images that you need to create, because there is no way to track the state of the application or the requirements based on which it is running either. So every time for hardware level virtualization, the situation is about similar to like booting a new local computer, right? And that creates a problem in terms of performance. In order to implement it as well, there is an issue with respect to the cost, okay? And then it is slow to initialize because you're booting it from the scratch, okay? And even if you're able to store all of the different virtual machine images, and that is going to be ranging in the thousands to the 10,000s if you look at a proper implementation, right? Then how do you keep a track of the commonality between the different virtual machine images or different virtual machine templates that is being stored, right? So that creates an overhead on the storage itself. Right? So how do you keep a track of all of those things? So the immediate solution that people understood to the drawbacks of hardware level implementation was, instead of trying to implement virtualization as a technology on the hardware with the hopes that things will be fast in terms of latency. And of course, remember that if you are able to implement it on the hardware level, then in terms of performance, you will get one of the best performance, right? But it is not always like that. And as we discussed, there are, of course, many challenges that is present there. So what people realize that instead of doing it on the hardware level, instead of implementing the technology on the hardware level, what we do is we try to implement that same ideology, but emulate it through the software, right? And the next layer of choice for implementing that as a software emulated technology was to basically put the virtualization layer on the OS and then share the available underlying resources based on whenever a user needs it, right? So all of the interaction or all of the implementation of the virtualization technology was essentially achieved through a single operating system's kernel, okay? And this type of implementation is formally known as a virtual execution environment, or in short, it is known as VE, or sometimes it is also called a virtual private system, or VPS, or simply known as containers, okay? But for a user, like the person who will be using the service, to them, these virtual execution environments, or VEs, will behave similar to as if they're using a real server or their own local system, right? So the OS level virtualizations and creation of virtual machines through OS level virtualization was thereby came to be known as the single OS image virtualization. Okay, so essentially it was enabled on top of a host operating system. Now you understand that the moment we talk about this, that the virtualization was implemented on top of the host operating system. So that means the architecture was you have the hardware, and then you have the host operating system, and then on top of this, VMs were being created. So this is basically the foundation towards the creation of type 2 hypervisors. Okay, so that's the architecture that we're going towards. And the idea, this whole conceptual notion was actually adopted for something that already existed. Okay, so this single OS image virtualization is actually drawing from a concept that we have also actually discussed, and it existed in the paradigm. Can somebody tell me what that is? This idea of a single OS image virtualization. Have you seen something which is similar to this notion? Anyone? No? So in computer clusters, that's the hint. Can somebody say now? So we discussed about the fact of single system image, right? Or the concept of SSI in computer clusters, right? So if you recall the features and the implementation design requirements for the single system image for developing computer clusters, the essence of a single OS image virtualization comes from that as well, right? So if you look at all of the different properties here, that the user sees it as a real server or their own local machines, and then you create separate containers where the users will be able to use it, they follow this notion of single system image. So that is where this idea of single OS image virtualization is coming from, right? So if you look at the architecture of the implementation itself, everything that is to the right of this borderline here is basically the implementation of the virtualization. Okay, so this is basically the hardware. So we don't have to be concerned about this portion here, but pay attention to how this implementation happens. So you have the network layer virtualization. Okay, so we don't have to discuss this in particular because we're only concerned about instantiating a virtual environment on top of a physical resource. You have the actual hardware as well. Okay, and then you have the host operating system that is essentially having a direct control of these hardwares and networking operations. Then on top of that, you have the hypervisor. Okay, so this is an example of the open virtualization layer. All right, so it can be implemented by some of the softwares that is available for us. And then on top of that, what you're creating or saving is basically the VM templates that can be used by the users, right? So these templates are basically some breakdown with respect to the different CPU power, RAM or memory powers, and then storage options that are available, both in terms of quantity and in terms of the type that you're looking at. So we are looking at either like one core, dual core, tri-core, or further, right? You're looking at different types of options here, like if you want to take a 2 GB, 4 GB, 8, 16, and so on and so forth. In terms of storage, you're looking at 1 GB of either hard disk drive. Nowadays, even solid state drives are available in the storage options and stuff like that. You also get to choose your own, you don't get to choose actually for this particular implementation, right? So essentially, that kind of segues into the drawbacks of this level of implementation, right? So anyways, so these templates saved all of these different configurations options that was available in order to instantiate different VMs. And then on top of that, this is where you create your containers or virtual private servers, right? And within that, you have all your different application softwares the different user access or user accounts that you can create. The users can control the identity management. And then in addition to that, you also have the directory structure, or basically the storage directory structures, which based on which the users can save their files, access their files, and it is directly kind of tied up with this underlying hardware resources that is there. So what are the drawbacks? Well, one of the basic drawbacks, we just talked about it when we were trying to discuss the configuration of current day cloud computing VM templates, is the fact that if you just simply implement this architecture, then all of the different containers will have to share the underlying host operating system. So that means if you have a Windows distribution on your physical machine, then all of the different containers will also have to use the Windows distribution. So that is why you see here inside these containers, there is no mentioning of any kind of guest OS. Okay, so this is kind of like not a foreshadowing, but like is there an opposite of foreshadowing? Like a pre-shadowing of why we said that this type of implementation results in containers, right? And that goes back to the definition of the differences between a hypervisor and a container itself, right? So here, this is one of the drawbacks that you will face, that if people had just used virtualization on the OS level as is, with the ideology being the fact that the virtualization layer of tracking and creating templates would be implemented on top of the host operating system, then all the different containers that the users will use will basically share the same host operating system's distribution, okay? So, however, if we did use this particular strategy of implementation, then it addressed the two challenges that was being faced by hardware level implementation of virtualization. So the first one is that we got rid of the slow initialization of VMs, okay? So we just created the templates and everything is ready. The operating system is ready. We don't have to kind of load up a new operating system within the environments. And as a result of that, the booting process basically speeds up, right? Also, since things are running on top of the operating system, and then there is a direct connection of these operating systems through the virtualization layer with these containers, then whatever is happening inside of the containers with respect to the execution were being tracked by this virtualization layer as along with the support of the host operating systems, right? So that is why there are two things that comes out of this. The first one is that the basic implementation of OS level virtualization addressed the challenges that was present in hardware level virtualization. So this is one of the main takeaways at this point for everybody, right? And going forward, what you have to realize that this implementation strategy in itself, or this architecture in itself, was not completely devoid of any kind of drawbacks, right? And the major drawback being that all of the different containers, okay, had to share the underlying host operating system's distribution, okay? So, of course, the discussion when it goes forward than this is something that how do we resolve this drawback, right? Because as you can understand, and as everybody can appreciate, that if you are just relying on the host operating system's distribution and basically dispensing that as a service to whatever container you are creating on top of it, then you will be limited with respect to how you can satisfy the choices of different users. And the choices of different users will vary, right? So for example, at one time window, you might be requiring the usage of a Windows system, right? And then later on down the line, you might want to switch to a Linux distribution, right? Or maybe a Macintosh distribution if you're developing something that is specific to the Mac environment, something along these lines, right? So user choices are not going to remain static. And then if you're saying that you can only use the underlying distribution operating system, right? The host operating system, then that also limits the resource sharing. So what it means, like, if you have a commodity hardware, if you bring 10 commodity hardwares, 5 of them or 6 of them are Windows, 3 of them are basically Linux, and then 1 of them is Mac, right? And then most of your users want Mac operating system at that point of time, then only a single physical resource will get a lot of strain, right? Or stress, whatever you want to call it. So that is a problem, right? And people did not kind of accept this as the final implementation of the architecture that needs to implement the directory, right? And the other problem that kind of resulted from this kind of architecture's implementation was the issue with the directory structure. Because the directory structure is directly influenced by the operating system's distribution on top of which the storage has been implemented. So that means if you're borrowing from the host operating system, then the user will see a directory structure that is specific to the underlying operating system, right? And this is a direct violation of the features of single system image design, right? Remember, if you recall, single system image design had like 9 different design criteria, right? And one of them is the transparency to the directory structure that the user will access. So regardless of whatever underlying physical resources is being used, the directory structure access should be universally applicable across all of the different virtual machines or different types of users who will be accessing the virtual machines, right? So that is a problem because now you cannot do that. If you take the VM, which is running on one underlying operating system's distribution and move it to another different operating system distribution, then that will create a problem with the root directory structure, okay? So these are some of the additional overheads that essentially resulted in canceling out the benefits that we had achieved from OS level virtualization over hardware level virtualization. So what was the solution? Well, the solution was something in between, right? So essentially what happened is that hardware level virtualization essentially didn't have much benefits to begin with, okay? When it was implemented through operating system virtualization, then it was able to address some of the challenges or most of the challenges that existed on the hardware level, but it also resulted in its own negative points, right? So in order to address this, and we know that the latency of implementation is the best if you are able to kind of modify the hardware and implement virtualization there. So what designers or architects decided is that they will still kind of adopt the idea of OS level virtualization, but the implementation will be on a layer that is not on the OS level or fully on the hardware level. And this layer of implementation was known as hardware assisted virtual machines, okay? So not hardware level virtualization, not OS level virtualization, but essentially what we call or what we come to know as the hardware assisted virtual machine. So the whole idea of hardware assisted VM implementation was the fact that certain tweaks, plug and play tweaks, was made to the existing commodity hardwares such that they are capable of supporting the virtualization which will be implemented on the software, okay? Addressing the overheads or the drawbacks of both the hardware level as well as the OS level, okay? So let's talk about the architecture that essentially was functionally developed in order to enable the implementation of hardware assisted virtual machines, right? So remember here, we're talking about a layer in between, okay? So this is not what the operating system does. Operating system is another software that is not a part of this layer, okay? And since you're not implementing any kind of virtualization within the hardware, there has to be another layer of software that implements this level of virtualization. Pay close attention to what we are talking about here. Initially, the option was to implement within the hardware itself. And this was a no-no because it had its own overhead problems. The second option was the operating system itself. And then it was suggested that you create the virtualization layer here, okay, on top of the OS, keep a track of the templates and the state of different VMs, and then create containers that can run the different applications, right, or different processes that was necessary. But the problem with this is the transparency in the access to the root directory structure. It also has the problem that all of the containers had to use the underlying distribution of the operating system, the host operating system. So the choice decision that was made for the design basically states that we want to implement it not on the OS level, but on the hardware level, but somewhere in between, right? So they still wanted to implement it using a software, but they wanted the benefits of the performance that comes from hardware level, right? So not having to have the operating system be the mediator in order to initialize any of the VMs on top of this. This software was the hypervisor. Okay, so that is where the notion of actually where the hypervisor came into being, why people wrote the software for hypervisor. This is where the discussion kind of led to, and people realized that they need another software that can essentially emulate or implement the process of virtualization by being capable of directly interacting with the hardware itself and not having to bother the operating system. Right? So this is the motivation behind how an hypervisor came into being, right? And we already discussed about the two different types of architecture of where you can keep this hypervisor. So if you keep this hypervisor between the OS and the actual hardware layer, then this becomes a type 1 hypervisor, okay? And if you take this hypervisor and put it on top of the host operating system, then that becomes a type 2 hypervisor, essentially, right? So then how does the hypervisor essentially manage its call? And you notice here that if you implement the type 1 hypervisor, it essentially addresses the issues, well, it addresses the issues through and through of operating system level virtualization, having to use the host operating system's distribution for all the containers. Because now what can happen, if you read between the lines, you will have the hardware here, okay? On top of that, you will have the hypervisor, the virtual machine manager. And now the virtual machine manager can create not containers, but actual virtual machines, which will have its own guest operating system, and everything else will kind of remains the same, right? And the root directory structure or the storage directory structure that was an issue with operating system level virtualization is now also resolved, because any kind of access to the storage will be done based on a call, okay, a process call through the hypervisor itself, okay? And these process calls are known as hypercalls, okay? So these hypercalls is available as not a service, but basically whenever the VMs, which is running its own version of guest operating system and apps, they want to access any of the underlying resources that is being directly managed by the hypervisor, then they, instead of the operating system or host operating system, they will have to interact with the resources through a hypervisor, right? And when you make a call, when a VM makes a call for resources to the hypervisor, it is known as a hypercall, right? So now, depending on how these hypervisors were implemented, functionally speaking, right, not in terms of architecture, right? So we discussed about the two different categories of hypervisors in terms of where you implement the hypervisor, right? There is also another discussion on how the hypervisors are implemented, right? Is the software part of it, right? Not the actual architectural part of it. So depending on how you implement the hypervisors, there are two different categories. The first one, and the more popular one, is known as the microkernel architecture. And one example of the microkernel architecture is the popular choice of Microsoft Hyper-V hypervisor, right? The Oracle OS ESX also falls into this. The Oracle VM also falls into this. And then you have another option, which is known as the monolithic architecture, right? And the example for that is the VMware Server Initialization, or ESX, okay? So essentially, the main distinction between these two different types of functional architectures is that the microkernel architecture essentially handles, okay, it is responsible for different basic and unchanging functions. Example of these different basics and unchanging functions are memory management and process scheduling. All other operations, which are dynamic in nature and might change from time to time, such as managing the device drivers of the actual hardwares, they are outside the control of the microkernel architecture. And in contrast to that, The monolithic architecture basically implements everything. So that is, it takes care of all the basic unchanging functions that needs to be supported for all VMs, as well as the dynamic operations such as access to the device drivers that is there, right? So if this is basically the discussion of microkernel versus monolithic architectures, how would you decide which one to use? Of course, any times when we have two different choices, basically we need to be able to think which one is suitable for what type of cases, right? So if you understand this, what type of metric would you use, or what type of analysis criteria would you use in order to make a decision between, let's say, if you're starting your own cloud computing organization, then should you implement a hypervisor that uses the microkernel architecture, or should you use a hypervisor that uses the monolithic architecture? Come on, speak up. So when you have to decide between the choices that is present for microkernel or monolithic architecture, what you have to keep in mind is essentially, at the end of the day, both of these two options are software, right? So if one of the softwares essentially manages only part of the components or part of the functionalities, then the size of the software that will be required to be written as code will be quite less compared to the monolithic architecture, because the monolithic architecture, essentially, its responsibility is to implement everything, right? So if you want to implement everything, then you have to write a larger piece of code in order to be able to execute that. So now the question is, if the microkernel architecture is only responsible for different unchangeable and basic functions, such as memory management or scheduling of the processes, when are these processes going to get what type of resources, then who is responsible for managing the device drivers, right? So that is an important thought that you should have at this point of time, that, okay, monolithic implements everything, no problem. So that means whatever functionality needs to be dispensed will be done by the hypervisor itself. You don't have to worry about who does what type of responsibilities, right? Or who executes what type of responsibility. But since here there is a division of responsibilities, that the microkernel hypervisor only is responsible for part of the operations that needs to be managed, then the immediate question that should follow at that point of time is essentially, who is then responsible or in charge of managing the device drivers or the underlying system resources? So that means if you make a call as a VM, okay, if a VM makes a call directly to, let's say, access the storage, or maybe increase its RAM or use a part of the RAM and stuff like that, or the IO devices, which is also a part of the underlying resources, right? Then who decides that, okay, I should give them the requested resource, or I should stop them from using it, or I should actually execute their requested resource and stuff like that. So this brings us to one of the most famous type of microkernel architectures that was initially designed at the very beginning, that was known as the Sen architecture. Okay, it was initially a Linux-based distribution, all right, written there. It was open source and it was developed by Cambridge University, all right. But now there are commercial variants of the Sen architecture itself, right? And that is known as, in the very popular Oracle VM. A lot of you might have heard this name as well, and a little less popular, but it's also quite well known in terms of commercially. It's known as the Citrix Sen-se, right? And this is a type 1, okay, microkernel architecture. All right, so type 1 because it is positioned directly on top of the hardware, and microkernel because the hypervisor is only responsible for the basic operations of the VMs, such as process scheduling, memory management, and those kind of things. And then somebody else, some other entity, is essentially responsible for controlling the access of the virtual machines on the hardware resources, right? And this is known as the entity that is responsible for actually dispensing these operations is known as domain zero or user zero, right? So essentially what happens during the booting process, when you actually implement the Zen hypervisor, before any user comes into the picture to begin with, right? There is a virtual machine environment, which is known as domain zero, that is booted up first. Okay. And domain zero has the capability to directly access the different device drivers or the underlying hardware resources that is available, okay, from the physical computer itself. After that, there is a separation of access control, right? And then all of the different user virtual machines are executed in what is known as domain U or domain users, right? And then you can have multiple virtual machines that can be initialized within domain. So anytime there is a virtual machine that is instantiated, it can be initialized based on whatever operating system the user chooses. And as a result of that, it is addressing the drawbacks of the operating system level virtualization. Okay, so you can either choose a Linux distribution, Windows, Mac, whatever you want, right? And on top of that, you can create different containers, okay, just as you can do inside any kind of virtual machine. If these virtual machines have a request that is with respect to process scheduling or memory management, then that request will be submitted in the form of a hypercall directly to the hypervisor, right? And the hypervisor will then do the scheduling and all the process management, and then it will respond back to the virtual machines itself, right? However, if there is a request to access the hardware devices or the device drivers, then the virtual machine will make a call that will be sent or forwarded to domain zero, which is basically you can think of it as the admin VM or the root VM. And then that domain zero will interact with the hardware devices, get the response back, and send it back to the requesting virtual machine, which belongs to domain U or the user domain, right? So as you can see here now, based on this architecture, which is a type 1 microkernel architecture, we have kind of addressed the problems with hardware level virtualization. We have also addressed the problems with respect to operating system level virtualization as well. Okay, so this is the problem. But of course, there is a major issue that you have to keep in mind in terms of security when you're looking at this type of microkernel architecture, is that you need to be very careful as how you protect this admin or root VM. Because since this domain zero, this virtual machine environment, has direct access to the hardware, and it is also responsible for managing the access to the hardware for all the user virtual machines that will be initialized on this physical resource, then you have to keep it secure. Okay, so you have to make sure that you declare very strong network access policies, network access control policies, different security policies, different types of privilege in terms of what can be executed and who can access this particular domain, right? So that is something that you have to keep in mind when you're working with a microkernel architecture. And monolithic takes care of everything, but the trade-off, if you're using the monolithic architecture, is that the size of the hypervisor is going to be very large, right? So that means the size of the software that needs to be written and implemented is going to be very large compared to the microkernel architecture. So because the initialization of the microkernel architecture is pretty easy to use, people generally go for the microkernel architecture and then implement very strong security policies for the domain zero environment to make sure that it is not vulnerable to any kind of outside or unauthorized accesses. Okay. So essentially, thereafter, we have to understand that, okay, the Zen hypervisor implements the microkernel architecture, and then the hypervisor enables the execution of these different virtual machines, right? But you need to also know thereafter is that how exactly virtualization is applied to the different essential hardware resources that is available or that needs to be used for all of the different user environments, right? So this again goes back to what you call it as the virtualization environment. You need to know that what is the different layers of a computer system, right? So what are the actual hardware resources that are available on any local computing devices, right? So you have the option for CPU. So these are technically the resources that is being virtualized. So you can also virtualize the memory, okay, which essentially is known as the RAM. CPU is basically the processors. And then you have the options for input-output virtualization. And then finally, you have the option for storage virtualization as well, right? So if we are going by this idea that we are going to be implementing the hardware-assisted virtualization layer, right, then how within that domain, right, of hardware-assisted virtualization layer, do you virtualize all of these different required physical resources and then provide it in a virtualized way to all of the different virtual machines that you are going to initialize, right? So essentially what we have to kind of learn from there is how to perform virtualization on these different physical resources, right? So starting off with CPU level virtualization, okay? The only way that a CPU architecture can be virtualized if the CPU or the processor is able to distinguish between privileged and unprivileged instructions in the user mode and the hypervisor mode. So what it's trying to say, to kind of boil it down into simple layman terms, is that remember the fact that in this architecture's implementation, the virtual machine manager is basically the supervisor, right? So the virtual machine manager essentially keeps a track of all of the privileged instructions. And then whatever the user mode or whatever the user VMs are running, they should be considered as unprivileged instructions. Okay. Similarly, the CPU should treat all the guest VMs and execute them in user mode, okay, so that they don't have access to the privileged instructions. And it should be able to allow the execution of the hypervisors in the admin mode or the supervised mode so that they do have access to the privileged instructions, right? So unless this behavior or this notion is supported by the actual CPU architecture, okay, then virtualization can be implemented. If you do not have this support, then you cannot implement virtualization, right? So the reason why you want to have this is because if, imagine from any of these user domains, if a call is made to the hardware resources, either for the processor execution or storage implementation or device IO instructions for the device IO, what you have to keep in mind is that if there is a control or a behavior sensitive request, right, that can potentially, let's say, harm the underlying physical resources, then that needs to be verified and tracked by the hypervisor. If that support is not available for the hypervisor, then essentially anybody can access these hardware devices and can execute any type of operation if there is no way to validate what request is being made, right? So that is why you need this kind of architectural support. Now, the problem is the current day x86 architectures that we know most of the commodity hardware uses nowadays were not initially designed keeping this implementation notion in mind. That is when people developed these commodity hardwares, they were only meant to be used as like personal computers, right? Nobody thought that people would pool those resources together, implement virtualization on top of that, and then try to execute different behaviors, right? Or resource sharing and stuff like that. They never thought of that, right? So it was very costly to come up with new architectures all from the scratch to support this architectural notion that is required for CPU virtualization. Okay, and this discussion kind of applies to all other type of physical resources as well, and we will see the final example when we are done discussing the individual levels of virtualization. So what the developers like Intel and AMD, who were responsible for developing these processor architectures, they came up with is instead of redefining and recreating their CPU architectures from the very scratch, what they will do is that they will provide some assistance to the hardware so that it can support this notion which is required to enable virtualization. So this is the whole idea of what we mean by hardware assistance, right? So they kept the original architecture, but they embedded a chip on top of that, which is responsible for enabling this particular architecture. That is the separation of the supervisor mode versus the user mode, allowing the hypervisor to run in the supervisor and allowing all the guest users to run, not allowing, but essentially making all the guest VMs run in the user mode, right? So the actual hardware remained as is, but a new chip technology or a new plug-and-play assistance was provided to the existing hardwares that enables the requirement for virtualization, okay? So for Intel, these chip technologies were known as VTX or VTI. Okay, and we will see the full picture of this, the big picture, in a few slides here. We will talk about this. So the next level of physical virtualization was basically memory virtualization, right? Now, memory virtualization is a fun thing to discuss, right? Because the first question is, how does memory allocation happen? That's the first question, and then that kind of takes us back to computer architecture, right? So if you think about computer architecture and computer organization classes, you have to ask yourself that if you have a local computer, right, like a personal computer, and if you think about how does memory allocation take place, what happens? You are never directly given access to the physical memory. That is, as a user, what we see, the directory structure, when we open, let's say, a file explorer or a directory explorer, we don't see the actual physical storage that is available in the machines, right? So what happens is, if this is the physical storage of the memory, the hard disk drive that is available or connected to your computer, what you see as a user is basically a virtual memory. Okay, and this is the virtual memory that we see as a user, which we are more familiar with, which is the root directory structure. But there is a mapping of the virtual memory to the physical memory and vice versa. So this is the mapping that is available. So this mapping enables the user to see what is happening. And then whenever the user executes any kind of request to store or retrieve data, that request is then mapped back to the physical memory. And then whatever information that you're trying to access is extracted from the physical memory and then shown through the virtual memory, right? So the virtual memory is essentially a user-friendly representation of the underlying physical memory. And this mapping takes place with the aid of these concepts that is known as the memory management unit, okay? And then a translational look-aside buffer, or the MMU and the TLB. So what you have to keep in mind is that for traditional machines, traditional local systems, there is this one-hop mapping that takes place, okay? So now, if you revisit the architecture of, let's say, a virtual environment, when we are implementing virtualization as a technology, so here you have your hardware, which consists of storage, CPU, memory, and all those things, okay? And then on top of that, let's say you have your hypervisor or VMN, okay? And then here you are initializing all of these different VMs. So you have VM1, you have VM2, and these are VMs in the domain U, or the user domain. We are not talking about the domain 0 or the admin VM that is responsible for directly interacting with the hardware, right? Here, you have your guest operating system, and then the root directory structure. And then different apps are running on top of this or inside this environment, right? So how would virtualization look like if you understand that this is how the memory allocation takes place in an actual physical machine, in your personal computers and stuff like that? Then if the environment kind of evolves from there into something like this, then what would the memory virtualization look like? Well, it will look something like this. And this is where the interesting thing happens, because this is the physical device right? This is the physical part controlled by this software, which is VMM. So this software doesn't have a direct view of the physical memory, because we just discussed about the fact that even in a standalone computer, which doesn't have any kind of virtualization, there is a one-hop mapping and there is a virtual memory layer on top of the physical memory layer. So that means here also at this very lowest level, we have the physical memory that sits on the hardware level. And then what the VM views that physical memory as is basically a layer of virtual memory. So the hypervisor in itself doesn't see the actual physical memory implementation. What the hypervisor interacts with is basically the virtual memory mapping of the actual physical memory that rests at the lowest level. Okay, so there is this one-hop mapping that happens here. But on top of that, you have to keep in mind that the user should see these environments as if it is a local computer. So that means to the user, within this virtual machine environment, there is also a layer of virtualized physical memory, which the user is able to view through its own layer of virtual memory. Don't get confused here. If you follow this discussion, it's kind of pretty interesting to note what is happening here. So note the fact that since the user needs to be transparent as to what is happening on the actual physical resources, then within the virtual machine environment, the user should be treated as if they have their own chunk of physical memory, and that can be viewed by the user through the virtual memory mapping, just as they would experience if they're using their own standalone computer. So there is another one-hop mapping that is present at or within the virtual machine itself. However, remember, this physical layer, which the user thinks that they have access to, is actually a virtualized storage layer, because this is present within the virtual machine environment. So it's not actually a physical piece of memory chunk, but it's a virtual piece of the physical memory chunk that has been allocated to that particular VM. So as a result of that, what happens when you are performing memory virtualization is basically there is a two-hop translation of memory addresses in order to reach this lowest level layer. So that means the user gives their request to the virtualized layer of the virtual physical memory within the virtual machine environment. This virtual physical machine, physical layer of memory that is present in every virtual environment is able to directly deal with this virtual layer, which the hypervisor is able to control, or the hypervisor is seeing. And then once hypervisor receives the request, it maps whatever request has been made to the actual physical location where the storage is actually present, right? So that is the fun part of it. So to look at it in a more, structured way, the guest OS has its own translation of virtual memory to physical memory. But remember, this physical memory is not actually the physical memory that is available to the VM, but it is a virtual layer of physical memory. Don't get confused there. Whereas the virtual machine manager, which can be responsible either through domain zero or in itself, it's a monolithic architecture, has its own mapping of physical memory to machine memory, which is the lowest layer itself that is residing on the hardware itself, right? So that means as a user, whenever they're trying to make a call to the memory, they will use their own virtual memory layer, which will be mapped to the physical memory. That physical memory will then be mapped through the hypervisor to the actual lowest level of machine memory of the hardware that underlies, right? So the second layer of translation that happens, that is in between the virtual machine and the hypervisor, it is known as shadow page tables. So we talked about the fact here that in a traditional computer, what enables the mapping between the virtual memory and the physical memory is the memory management unit and the translational look-aside buffer, right? It creates these page tables, which can then be loaded to the RAM, and then whatever content is there is basically executed, right? Remember, in computer architecture or in some of the operating system, you learned about the concept of pages, and different page sizes are available, right? So you can have 4K page size, 8K page size, 16K page size. We also discussed about this in databases, because database architecture, when it comes to about implementing transaction locks, you can implement it as page locks. Okay. So page is basically the size of storage in the memory, right? So whatever content is present in this 4K page size is essentially brought into the RAM, and then it gets executed, right? So either it is storage or processing instructions and stuff like that. All right. So this part of the page tables that is present at the lowest level, that is between the hypervisor and the machine memory, are known as shadow page tables. So there is two layers of translations that takes place in order to support memory virtualization. Okay. And then finally, you have the availability or the implementation of input-output virtualization, right? So there are three different ways in which you can implement input-output virtualization. So the first one is you do a full device emulation. Okay, so that means if you have a standalone local computer, the way you can use all of your different peripheral devices like keyboard, mice, and stuff like that, you will have the same behavior from within the virtual environment itself. Okay, if you think of an example of full device emulation, right? If you implement a hosted hypervisor, okay, so that means it's a type 2 hypervisor. This is basically an example of this is the VM player, okay, which can be installed in any of our personal computers, and then we can load an image of Linux or any other operating systems distribution, and we can run that operating system. So when the virtualization is implemented, when you're within that VM environment of VM player and then using your guest operating system, that essentially always uses this full device emulation, because you still use the keyboard that is attached to the actual physical device, but you're controlling the behavior or the operations within your virtual machine environment, right? So that is what full device emulation means. Then you have a partial virtualization, which is technically known as para-virtualization. Okay, so what it follows, the ideology it follows in order to implement the virtualization is kind of in the fact of a split driver model. So the split driver model is categorized into a front-end driver and then a back-end driver. So the front-end driver runs within the user domain, and the back-end driver essentially runs within domain 0 or the admin VM. Okay, and then there is a block of shared memory which enables the interaction between the discussions or the calls that needs to happen between the front end and the back end. Okay, so any kind of guest operating system resources that will be interacted or handled by the front end. So essentially, this kind of goes back again to the separation of responsibilities and access controls that is present between the user domain and domain 0. Okay, and then if you have a backend, that backend will actually be responsible for interacting with the IO devices and making sure the sharing of the IO devices can take place between multiple VMs requesting the resources, right? And then you have the direct input-output operations. So instead of emulating these different types of operations, the VMs can directly access the IO devices, okay? So typically you don't see a direct IO implementation for everyday virtual machine implementation that uses commodity hardwares. Essentially, if you're looking at mainframe computers for very large organizations or companies, that is the instance where you can find examples of direct IO. So otherwise, mostly what we will be looking at is either a full device emulation or a partial virtualization, which is split. The responsibility is split between a front end and a back end. The front end essentially is accessed by the user domain. So they submit their request to the front end, and the back end essentially is in control of the admin VM, which can directly talk with the device IO drivers, okay, IO drivers. And then there is a shared block of memory that enables the interaction between the front end and the back end, okay? So if you bring all of this together, that is, if you bring all of these virtualization technologies together, what you need to note is that for every level of virtualization, that is either you're doing an IO virtualization or you're doing a memory virtualization or a CPU virtualization, the hardware makers have provided additional technologies such that the hypervisors can actually implement the virtualization technology outside of the OS level as well as the hardware level, right? So for example, here, for processor levels, Intel has provided these two processing support technologies, these two hardware support that is known as VTX and VTI. In addition to that, there is a support for the device drivers, that is VTT. The memory is supported by this page table, okay, the support that is provided. And the VTD technology, that the chip that is enabling the IO device virtualization, also allows any kind of hypervisor to be able to interact with the memory that is present on the device. So you also have a support technology for the actual physical storage and network, which is supported by VTC. Okay, so the important takeaway here is that you need to not remember or memorize the name itself, but you need to understand the flow of logic, right? The conceptual logic of where did the inception of the implementation of virtualization technology start, right? And how did it reach to this point, right? So all of this discussion requires you to understand many different technologies or many different concepts, right? And that concept is basically the difference between hardware level virtualization versus OS level virtualization. What was the benefits and what was the drawbacks? How those benefits and drawbacks led to the conception of hardware assisted implementation of virtualization technology. Okay. What are the two different architectures of hypervisors from a functional standpoint and not from a positioning standpoint in the architecture? So there are microkernel architectures, and then you have monolithic architecture, and what is the difference between the two, right? And to have an understanding of which one to use in which scenarios, and then finally understand how different CPU, memory, and IO level virtualization is implemented when it comes to hardware assisted virtualization. That is the main thing. And then to get an understanding of what this architecture means, right? So it takes care of all of the overhead that is present in the software-based implementation of virtualization, and then provides the assistance of hardware wherever it is necessary. Okay, sometimes it won't be necessary, but sometimes when it is necessary. So for example, a case in point here, a very good case in point here was basically this CPU virtualization example, right? Where it clearly states that you cannot virtualize a CPU architecture unless there is a division of access control where the hypervisor gets to run in the supervisor mode and the CPU gets to run in a user mode. Okay, so that is something that is assisted on the hardware, right? It's not a software emulation anymore. The hardware makers essentially allowed the creation of these different chits, which enables the virtualization and then allows for two different divisions where one gets to run on a supervised mode, one gets to run on a user mode, right? So this wraps up the second chapter, okay, which is basically virtualization technology, or essentially introduction to virtualization technology. Okay, what follows hereafter is, now that we understand computer clusters, now that we understand the different aspects of virtualization as a technology, how do we take these two concepts that we have learned, that is computer cluster and virtualization technology, and make it into something that is known as virtual clusters itself, right? So that means, how do we improve further resource sharing? How do we improve resource allocation on our computer cluster, which essentially forms the backbone of cloud computing, right? So in the next chapter, in the next class from Monday onwards, we will discuss about these different virtual clusters and how resource management is performed on these different computer clusters, right? So once that is done, once the virtual cluster and resource management discussion is done, that will essentially lead to the discussion of how to house or how to kind of set up these different virtual clusters, these servers of virtual clusters, right? That essentially came to be known as a data center, that we call in today's day and age, what we know as a data center was basically a housing mechanism, a maintenance mechanism of kind of storing and then kind of performing any kind of update or any kind of maintenance activities on these different physical machines, on top of which virtualization was running, right? So we will talk about that in the next class. So what will follow from this point after, since we have already stopped or finished the discussion on chapter 2, which is virtualization itself, sometime in the next week, I will post the quiz for it as well. Okay, so please make sure that you will get probably about a week's time to finish the quiz. So please make sure to do so within the deadline. Okay, it only takes 10 to 15 minutes tops for 5 questions. You have seen the initial format. And then once this is done, then we can start our discussion about the basics of cloud computing. And then we will start discussing our introduction to Amazon Web Services. Okay, so I will stop the recording and the lecture for today at this point, and we'll take any questions that you may have.